Okay, so I have a very serious scenario for you. I want you to close your eyes. You are 6 years old again.
Uh-oh.
You are sitting right in the middle of a classroom. The teacher is up front, just droning on about times tables, and, she has eyes like a hawk.
Oh, I remember that pressure.
Yeah.
Sweaty palms. The stakes are incredibly high.
The highest. But you have this burning life or death secret you need to tell your best friend who is sitting all the way across the room.
Right.
And here's the problem. It's not just about not getting caught. It's about getting the message there intact.
Yeah.
You can't just throw a paper airplane because, I don't know, the ceiling fan might blow it off course. You can't whisper because the kid next to you might mishear it.
And then tell everyone you said something completely different.
Exactly. You don't want "I like your hat" to turn into "I bite your bat."
That changes the friendship dynamic significantly.
It really does. So the question is, how do you get that secret note across a noisy, dangerous classroom perfectly? And I mean perfectly. No mistakes.
Well, it sounds like a playground problem, but you've actually just described the fundamental problem of the entire information age.
Really?
Figuring out how to pass that note is exactly how the internet, how space probes, and how streaming video all work.
Which brings us to the subject of today's deep dive. We are looking at a paper from 1948 by a guy named Claude Shannon. It's called A Mathematical Theory of Communication. And frankly, when I first looked at this thing, it looked scary. It's full of calculus and theorems.
It is a dense titan of a document. It's basically the Magna Carta of the digital world. Before this paper, information wasn't even something we thought we could measure.
It was just stuff.
Just stuff people said. Exactly.
But we're going to try something different today. We aren't going to read the calculus. We are going to explain this entire theory as if we're teaching a 6-year-old how to pass that note in class.
Already.
We're going to swap the engineering jargon for, like, guess who and telephone.
I love it. Because at its core, Shannon's paper is a guide to beating the noise that tries to ruin all our messages.
So let's open the manual. Shannon starts with a diagram, figure 1. It looks like a roadmap.
This is his general communication system. For engineers, it's wires and boxes. But for our 6-year-old, let's map it right onto the classroom.
Okay, step 1. The box on the far left. The information source.
That's you, the kid with the secret. The source is the brain where the message is born.
Got it. Then the message goes to the transmitter.
In the classroom, that's your hand holding the pencil. It's the thing that turns the thought, which is invisible, into something physical, like ink on paper. It encodes it.
Then the message has to travel, and Shannon calls this the channel.
The channel is the dangerous part. It's the space between the desks. It's the air carrying your whisper. It's simply the path the message takes.
And finally, it hits the receiver, your friend's eyes, and the destination, which is your friend's brain.
It seems so simple, right? Breaking it down into 5 stops: source, transmitter, channel, receiver, destination. But this is a massive shift. Before this, engineers tried to fix everything at once. Shannon said, no, look at the channel separately. Look at the source separately.
But here is where my brain started to hurt a little bit, and I need you to help me out. Shannon wanted to do math on this.
Right.
But how do you weigh a message? I can weigh a gallon of milk. I can measure a mile of road. But how do you measure "I like your hat"?
This is the genius moment. He realized that information isn't about what you say. It's about what you could have said. It's about surprise.
Surprise.
Think about it. If I hand you a note and you already know exactly what's written on it, did I give you any information?
No, I mean, I already knew it.
Right. Information is the resolution of uncertainty. It's narrowing down the possibilities. And Shannon needed a unit to measure that narrowing down. He called it the bit.
The bit, which I learned from the note stands for binary digit, named by Mr. J.W. Ticky.
That's the one.
But let's stick to the 6-year-old version. What is a bit?
A bit is just a single choice between 2 things. Yes or no. Heads or tails. On or off.
Okay, so let's say I'm playing 20 questions with the kid in the classroom. I'm thinking of an animal.
Great example. If you just tell me the animal, that's a lot of information. But let's break it down into bits. My first question. Is it a mammal?
Well, that cuts the whole universe of animals in half.
And that is 1 bit of information. Yes, it's a mammal. Now I've thrown away all the birds and the fish and the lizards. I've narrowed the search. So my next question. Is it bigger than a dog?
That cuts the mammals in half again.
And that's another bit. Every single time you answer a yes-no question that cuts the possibilities in half, you are transmitting 1 bit of information.
So if I have a really complicated secret like The treasure is buried under the third oak tree at noon. That's just a whole lot of yes-no questions stacked up.
Precisely. Shannon showed that everything, a photo, a song, a text message, can be boiled down to a long, long string of yes and no. A billion light switches flipping up and down.
Which is wild. The whole world is just a pile of choices. But let's go back to our classroom. I've written my note, I've got my bits, I slide the note across the floor. But there's a villain in the diagram.
The villain. The noise source.
In the paper, it's a box attacking the channel. Now, to a kid, noise is just, loud banging. But Shannon means something else, doesn't he?
He does. In this theory, noise is anything that messes with the signal while it's traveling. If you whisper and the janitor turns on a vacuum cleaner, that's noise.
Or if I slide the note and the teacher steps on it with a muddy shoe and it smears the ink.
Exactly. That mud is noise. It changes the signal. You wrote cat, but the mud covers the C, and your friend thinks it looks like bat.
This is the worst case scenario. The message is corrupted. Now, before Shannon, I feel like the solution to this was just shout louder.
That was the old way. That's the analog mindset. If the radio has static, you crank up the power. If the teacher is loud, you scream the secret.
But shouting takes energy.
And eventually, you can't shout loud enough. The signal always degrades. Think of making a photocopy of a photocopy of a photocopy.
Right, it gets fuzzier and fuzzier.
Shannon said. Stop trying to shout louder.
Yeah.
You need to be smarter. We need to measure the confusion. He called this equivocation.
Whoa. That is a $5 word for a 6-year-old.
It just means maybe. If your friend looks at the muddy note and says, I'm 50% sure this says cat, but 50% sure it says bat, that is high equivocation, high confusion.
So we want zero confusion. We want zero maybe.
We want the friend to look at the muddy note and say, I know 100% that this says cat, even though there's mud on it.
How is that even possible? I mean, if the ink is gone, it's gone. You can't magically bring it back.
You can if you use the patterns of the language itself. This brings us to my favorite part of the paper, the section on approximations to English.
Oh, this was my favorite part too. Shannon basically admits that English is a code we've all agreed on, and it's super, super predictable.
It is. Letters aren't random. If you were just pulling Scrabble tiles out of a bag, you'd get a total mess. But in a real sentence, if I show you the letter T, what is the most likely letter to come next?
H. Almost always.
And if I show you Q?
U. It's basically glued to it.
So, because we have these rules, we can guess. Shannon actually played a game in the paper where he generated fake English using math probabilities.
I have to read these. I want to try to pronounce them. He started with zero order, which is just total randomness. He rolled the dice on the alphabet.
And what did that sound like?
It sounds like an elf having a stroke. X, F, O, M, R, X, K, H, R, J, F, J, U, J.
Catchy.
Then he tried first order. So he put more E's and T's in, because we use them more, but he didn't put them in order. O, C, R, H, L, I, R, G, W, R, N, meal.
Okay, it's getting a little more pronounceable. In meal could be a wizard's name, maybe?
Then he used diagrams, looking at pairs of letters that like to sit together. Anaidi Antvoetnies are.
Ant out niece? That sounds like someone mumbling in their sleep. You can almost hear the cadence of speech in there.
And finally, he did word-level approximation. He just strung random words together based on how often they follow each other. The head and in frontal attack on an English writer.
Wow. That sounds like a headline. It makes grammatical sense, even though it means absolutely nothing.
It's spooky. It sounds like a real person, and math wrote that.
And this proves that English has structure. And Shannon called that structure redundancy.
Redundancy. That usually means useless extra stuff. Like if I say ATM machine, I'm saying machine twice.
But in engineering, redundancy is a safety net. Shannon calculated that English is about 50% redundant.
Meaning I can delete half the letters.
Yes. Let's play a game with you, the listener. If I write the message, P's air, PSLLRT, and I leave out all those vowels.
Please pass the salt. I can read it instantly.
How? The letters are missing. The noise ate them.
My brain it fills them in because I know the pattern.
Exactly. That is redundancy. It is the bottle wrap around the message. It protects the secret note. Even if the teacher steps on half the words, the extra structure helps you guess the rest.
Okay, that makes sense for English. But what if I'm sending numbers? Or what if the noise is really bad, like the vacuum cleaner is roaring and I can't guess?
Then guessing isn't enough. You need error correction.
This is the part where Shannon stops being an observer and starts being a magician. How do we fix a mistake that has already happened?
We add check bits.
Check bits. Okay, explain this like I'm sitting at the desk.
Okay. Imagine you need to send a specific block of 4 numbers to your friend, But instead of just sending 4, you decide to send 7.
Why? I'm wasting time sending 3 extra numbers.
Those 3 extra numbers are spies. They are tattletales.
Who are they telling on?
The other numbers, they're set up using a special rule, often called a parity check. Let's keep it simple. Imagine you tell your friend, hey, every time I send you a group of blocks, the total number of blocks has to be an even number.
Okay, the even club. No odd numbers allowed in the club.
So you send your blocks, but on the way, the noise monster kicks 1 block over. It changes a yes to a no. Suddenly, the total number of blocks is ODD.
So my friend gets the message, counts the blocks, sees it's an odd number, and says, wait a minute, you broke the rules. Something is wrong.
Right. Now, that just tells you there is an error. But Shannon and another guy, Richard Hamming, they took it further. They arranged these spy bits in such a clever, overlapping way that they don't just say there is an error, they scream, the error is in the 3rd position.
Wait, hold on. You're telling me that by adding a few extra numbers, the receiver can figure out exactly which number got broken and just flip it back?
Yes. It's like the teacher watching you take a test. Instead of just marking a question wrong, she points to the exact digit you messed up so you can erase it and write the right one.
So I don't have to resend the whole message?
Nope. The message heals itself.
That sounds like actual magic. That means I can send a message through a storm, have pieces of it get destroyed, and the receiver can rebuild it perfectly using these spy bits.
That is exactly what happens when your computer reads a scratched DVD, or when a space probe sends a photo from Mars. The signal is weak and full of static, but the check bits reconstruct the photo perfectly.
Incredible. So we have bits to measure the talk, we have a redundancy to help us guess, we have check bits to fix the mistakes, we're ready to pass the note. But wait, there's a catch, isn't there? There's always a catch.
There is a speed limit.
A speed limit on talking.
Shannon called it channel capacity. He used the letter C.
C for capacity, okay.
He proved that every channel, whether it's a wire, a fiber optic cable, or passing a note in class, has a hard limit on how many bits it can handle per second.
Okay, but limits are meant to be broken, right? If I really need to get the secret out, I'll just talk faster. I'll shove the note harder.
And that is where you crash. Think of the channel like a water pipe.
I'm picturing a garden hose.
Perfect. You can pour water information through that hose smoothly. That's the capacity. But what happens if you try to force the entire Atlantic Ocean through that garden hose in 1 second?
The hose bursts. Water sprays everywhere, a giant mess.
That spray is errors. Information lost forever. Shannon proved a fundamental theorem. If you send information slower than the capacity, you can get perfect, error-free communication.
Perfect. Like 0 mistakes.
As close to 0 as you want. You can beat the noise completely. But the second you try to go faster than the speed limit,
the pipe bursts.
The errors skyrocket. And no amount of check bits or guessing will save you. You cannot understand the message. It is mathematically impossible.
So it's not a suggestion, it's a law of physics, like gravity.
It is. The fundamental theorem of channel capacity defines the boundary of what is possible in our universe.
That is heavy for a classroom note. So let's wrap this up for our learner. We started with a secret note in a noisy class.
We learned that we can break communication down. Source, transmitter, channel, receiver.
We learned that information is just a series of yes-no choices called bits.
And we learned that to beat the noise monster, we use the natural patterns of language redundancy.
And if that fails, we use check bits, math spies, to fix the errors without asking for help.
But we have to respect the speed limit of the pipe.
That is a lot of tools for a 6-year-old. But why does this matter to the person listening right now? Why should you care about 1948 math?
Because you are using it right now, literally, this second. The audio of our voices is a stream of bits fighting against the noise of the internet.
And the fact that my voice sounds clear?
That's Shannon. Your phone is doing millions of parity checks every second. It's using redundancy to fill in the gaps when the signal drops. We moved from an analog world where things got fuzzy and distorted, to a digital world where we can make perfect copies forever.
It's the difference between a photocopy and a clone.
Exactly. The internet is just a billion people passing notes in a very, very noisy classroom. And it only works because Claude Shannon wrote the instruction manual.
I'll never look at a text message the same way again. It's a little miracle of error-correcting math.
It really is.
Now, before we let you go, we like to leave you with something to chew on. A little provocative thought.
Right. So we talked about how English is 50% redundant, how Q demands U, and how math can predict the next word in a sentence.
Yeah.
Well, think about the texts you send. The autocomplete bar on your phone is pretty good at guessing what you're going to say, isn't it?
Sometimes it's too good. It finishes my sentences for me.
So if a simple math equation can predict your next word, and if your language is following a strict set of probability rules, it makes you wonder.
Wonder what?
Are you really choosing your words freely? Or are you just executing a mathematical algorithm? Are you writing the note, or is the probability of the English language writing you?
Oh man, am I just a very advanced speak and spell?
We'll let you decide.
Thanks for deep diving with us. Keep your signals clear, everyone. We'll see you next time.